RNS configuration. Now, it's important to be able to tell the reader what the structure of your molecule is by simply just typing out the name. And that's where the RNS configuration come in. So let's take an example. Say we have, I don't know, let's do something interesting. How about an amino acid? So there's an amino acid. And here's an amino acid. There we go. So this amino acid is alanine. This amino acid is alanine. Only one of them is natural, though. Alanine is an amino acid found in your body. Only one of them is the natural amino acid. But which one? Well, you could look it up and find out, or you could just assign RNS. Okay, one of them is natural, the other one is not. But now, on a label on a bottle, you can't draw structure. I mean, you can, but no one's going to understand it. You need to draw or write the name of what it is. Is it this alanine or that alanine? And that's where the RNS configuration comes in, because there's an R alanine and there's an S alanine. And that's what we're going to learn how to do today. We're going to learn how to assign what's called configuration. Is it the R configuration or is it the S configuration? And that's what we're going to learn in this part of the video. Of course, there's rules. Kahn, Ingold, Prelog have a ton of rules. And enantiomers have different spatial arrangements. So they're different in three-dimensional space. Okay, we've already seen that. You can take, your hand, try to overlap it onto the other one. You can't, because they're different in three-dimensional space. Okay? There's two possible spatial arrangements for enantiomers. And that's why there's only two of them. So you have a pair. They always come in pairs. And those will be called configurations. No problem. Each asymmetric carbon atom is lettered R or S depending on its three-dimensional configuration. It all depends on that. Okay? So Kahn, Ingold, and Prelog have given us a great roadmap we can use to figure out, is this configuration R or is this configuration S? And everybody follows Kahn, Ingold, Prelog rules when doing this. So we all should be able to take your name, your configuration in the molecule name, and draw the molecule exactly the way it should be, just because we're all following the same convention, because it's the most widely used convention out there. All right. When assigning RNS, we have to assign what's called relative priority. And it's 1 through 4. The priorities run 1 through 4. Okay? Now, group 1 has the priority group 1. Group 2 has the priority group 2. Group 3 is 3. And group 4 is 4. So that's how it goes. The top priority is 1. The last priority is 4. Now, how do we assign priority? It's very simple. It's assigned via atomic number. Assigned via atomic number. I did not say atomic mass. I said atomic number. Okay, that's the key. It's atomic number that assigns priority. So, for example, if I had fluorine versus bromine and I want to assign priority, bromine has a higher priority. It has a higher atomic number. If I wanted to assign carbon versus hydrogen, carbon gets the priority because carbon has a higher atomic number. Very simple. So here we go. Here's our first example of assigning priorities. Now, this one is priority group 1. This is priority group 2. This is priority group 3. And this is priority group 4. Now, how did I get there? It's very easy. What I do is I find the chiral carbon. It's right here. And I jump out from the chiral carbon through all bonds, one atom. I just jump out one atom. So I'm here. I'm going to jump out to fluorine. So what I like to do is put maybe a little dot. because that's where I'm considering. So I'm jumping out to carbon here. So I put a little dot. Now these dots aren't free radicals. It's just me keeping track of where I am in my assignments. You start at the chiral center and you jump out through the bond to the first atom, or the next atom that's attached to the chiral center. So jump out from the carbon to the nitrogen. So now what I'm doing is I'm going to be considering fluorine versus carbon versus hydrogen versus nitrogen. So I have, when I jump, because I'm not considering entire groups, I'm just considering atoms. I'm here, this is my chiral center, I jump out through the bond in all the directions of the bonds, one atom. I don't care about these hydrogens on here, I don't care about the hydrogens on here, I only care about the nitrogen, fluorine, carbon, and hydrogen. That's all I care about. Don't worry about the atomic weights of the groups, don't worry about any of that nonsense. Only worry about the atoms you're on. So I started here, you jump out one atom in each direction of bonds. Just do that. I find that I'm on a fluorine, I'm on a carbon, I'm on a hydrogen, and I'm on a nitrogen. So now I consider these four and these four only. Which atom has the highest atomic number? If you look at the periodic table, you'll find out it's fluorine. Fluorine has the highest atomic number of these four atoms. So fluorine became priority group 1. So fluorine is gone. I've already assigned fluorine. Who has the next highest atomic number? You'll look at the periodic table and you'll find it's nitrogen. Nitrogen has the next highest atomic number, so it's priority group number 2. So now I have carbon and hydrogen left, and that's it. Well, carbon has a higher atomic number, so carbon has priority group 3, and hydrogen has priority group 4. Almost, well, I shouldn't say almost. Always, when you have a hydrogen on your chiral carbon, hydrogen is always going to be group 4. Because hydrogen, if the hydrogen is attached to the chiral carbon, though, the hydrogen must be directly bonded to the chiral carbon. It's priority group 4 because there's no other atom that has a lower atomic number than hydrogen. Now, here's the problem with Kohn-Ingold, not the problem, the challenge. Here's the challenge with the Kohn-Ingold-Prelog rules. What if there's a tie? What if you go to the chiral center and you jump out one atom and you have two of the same atoms? How do we handle that? Very, very simple. So here's a great example of how we would apply the tiebreaker rules or the tiebreaker methodology. It's very simple. So find the chiral carbon. So the chiral carbon is right here. That's the carbon that has 4 different groups attached to it. So just like before, I said find the chiral carbon and jump out one atom in all directions. Just one. So I'm jumping out, I'm finding that there's an oxygen, a hydrogen, a carbon, and a carbon. Jump out one atom through the bonds in all directions. It's one atom, just one atom. And I'll find there's an oxygen versus hydrogen. So oxygen, hydrogen, carbon versus carbon. Well, right off the top, I can assign priority group 1 to oxygen because we know oxygen, if we look at the periodic table, has the highest atomic number. So priority group 1 is this group right here. That's priority group 1. So we can get rid of oxygen. So now it's hydrogen versus carbon versus carbon. Well, hydrogen has the lowest atomic number, so it has to be priority group 4. And you're going to find this when you're doing these kind of questions, that almost always 1 and 4 are simple. Not always, but almost always. 1 and 4 are very simple. Assign them, just get rid of them. They're already, okay, we got it. Hydrogen's 4, oxygen's 1. That was simple. The challenge is almost always with 2 and 3, because now we have 2 of the same atom. Can't assign priority groups there. We have to jump out one more atom. So you keep jumping out until you find a difference. Okay? Keep jumping away from the chiral center until you find a difference. So we are here and here now. There's a tie. We jump out one more atom until we find a difference. So from this carbon, I can go hydrogen, hydrogen, hydrogen. So it doesn't matter where I jump, I find a hydrogen. So let's just write that down. Hydrogen from this group here versus, so from this carbon, I can jump out to hydrogen, hydrogen, or carbon. So there's my difference. Sorry, I guess I'm off the screen there. Sorry about that. So hydrogen versus, and this hydrogen comes from here. So I jumped out to here, let's say. From here, I can jump out to hydrogen, hydrogen, or carbon. So that's where I'm going to jump to. I'm going to jump to carbon because that's where the difference is. So it's going to be hydrogen versus carbon. So we know that carbon has the higher atomic number. So this group will be group number 2. And this will be group number 3. Okay? And that's how you would assign it with a tiebreaker. Tiebreakers, they're not hard really. Once you start working with tiebreakers, you'll start getting the habit. So this is how you do it. This is how you do it. This is how you do it. Now, students will often try to shortcut this. They'll start saying, well, this group is bigger, therefore it has to be higher priority. Be very careful with that. There's lots of ways to make that not work. Okay? Now, it works a lot when you just say, okay, this group's bigger, so therefore it's higher priority. That works a lot if you know when it doesn't work and you can, recognize when it doesn't work and fix it. If I was a student in this class trying to get an A, I wouldn't mess around with shortcuts. I would just follow the procedure, get it right every time. All right? Multiple bonds. Now, how do we treat multiple bonds using the Kohn-Ingold-Prelog system? This is challenging, but it's also very simple. Now, here's how it works. Let's say we have a molecule like this. We want to assign priority groups to that. Well, everyone, I think, in this room will agree that this is 1, and that's 4. Hydrogen's always 4 if it's attached to the chiral center. This is the chiral carbon. I jumped out 1 atom, oxygen, hydrogen, carbon, and carbon. So there's a tie. There's a tie between this one and that one. So a carbon here and a carbon here. But now what do? We have multiple bonds. How does Kohn-Ingold-Prelog say to handle the multiple bond situation? They say to look at a double bond or a triple bond as if the following. Okay, so try to follow with me. The double bond, and R, remember, is the rest of the molecule. So that's what we're trying to determine. We're trying to examine this alkene. Kohn-Ingold-Prelog say to imagine it looks like this. Now, it doesn't look like this. This is not any chemistry here. Nothing's being broken. Nothing's being made. It's only a tool or a thought exercise to help you understand how to examine these molecules with multiple bonds. So let's just draw it like this. So here's the R group where the chiral center is. There's the carbon. Let's call that carbon number 1, and that's carbon number 2. So there is carbon number 1 and carbon number 2. No problem so far. And if you look at carbon number 1, you say, okay, carbon number 1 is bonded to R, which it is here, and bonded to H. So let's draw a hydrogen on carbon number 1. So carbon number 1 now has a hydrogen. Carbon number 1 is also bonded to carbon number 2, and there it is. But if you think about it, and you think about it this way, carbon number 1 is bonded to carbon twice. It's bonded to carbon twice. It happens to be the same carbon, but it is bonded to carbon twice. So Kohn-Ingold-Prelog say to think of it like this, that this carbon is bonded to an R group where the chiral center is, a hydrogen, and 2 carbons. So this carbon is bonded to 2 carbons. That's how they say to think about it. Now go out to carbon number 2. Carbon number 2 has 2 hydrogens on it. And it's bonded to carbon number 1, which we have here, no problem. But remember, this carbon is bonded to carbon twice. So that's how Kahn, Ingold, Prelog say you should examine a double bond, just like that. What about the triple bond? No problem. Same ideas, different look, but same ideas. Let's call this carbon number 1, carbon number 2. So now when you're going to break this down, carbon number 1, carbon number 2. Everybody here will agree carbon number 1 is bonded to the R group. No problem. No problem. Everybody else will also agree, I think, that carbon number 1 is bonded to carbon 3 times. So carbon number 1 is bonded to this carbon 3 times. Kahn, Ingold, Prelog say to look at it like this. There's 1 bond to carbon, 2 bonds to carbon, 3 bonds to carbon. Now, this is not at all how it looks in reality. This is how Kahn, Ingold, and Prelog are saying when you're assigning priorities, examine it as if it were this. Okay? So now carbon number 2 is bonded to hydrogen. So let's draw that in. And it's bonded to carbon 3 times. So there's 1 bond to carbon. And there's the other 2. So this is how Kahn, Ingold, and Prelog say to examine multiple bonded species to assign priority. Now again, this does not exist in a flask. This does not exist in a flask. It's simply a tool to help assign priority. So let's use it. So we're here and we're here. So we jumped out 1 atom. We're here and here. So here and here. That's where we are right now, and that's what we're considering. We have 2 carbons, same, can't do anything with it, move on to the next one. So in essence, we're here and here. Okay? So Kahn, Ingold, Prelog say, when there's a tie, jump out 1 more atom until you find a difference. So from here, we can go to hydrogen, carbon, or carbon. So hydrogen, carbon, or carbon. So we can go to here, here, or here. From here, we can jump out to carbon, carbon, or carbon. So it becomes pretty clear, pretty fast, that this carbon and that carbon, no difference. This carbon and this carbon, no difference. This carbon versus that hydrogen, there's a difference. Carbon is a higher priority than hydrogen, so this is group number 2, and this is group number 3. That's how you do it. That's how Kahn, Ingold, and Prelog say to assign priority when there's multiple bonded species. Okay? It's challenging because it's weird. It's not hard, though. It's just strange. You all can do this. You all have the ability. Maybe rewatch this part of the video again. Try to figure out how I did this. It's very simple once you get the hang of it. Now, once we've assigned priorities, we need to assign R versus S. Now, when doing this, you have to kind of use your finger or use a pen or use something. And what you do is you count between groups 1 and groups 3. But here's the kicker, and here's the real problem and the real secret. Kahn, Ingold, and Prelog say, before assigning R and S, the low priority group, group number 4, must be facing away from you. That's the key. The low priority group, it does not always have to be hydrogen. A lot of times it is, but it doesn't have to be. The low priority group must face away from you. So here, luckily, the hydrogen is already facing away from me. So the low priority group is already facing the back. Now, take your pen or pencil, starting at group number 1, draw an arrow to group number 2, and then an arrow to group number 3, and then an arrow back to 1, and then keep retracing those steps. And you're going to see that your pen or pencil, in my case the laser pointer, is going counterclockwise. Counterclockwise. So this is the S configuration. The S configuration, because my marker was going counterclockwise. That's how you do it. Once you assign priority, move priority group 4 to the back if it's not already there. Count from 1 to 2 to 3 back to 1. 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 That's how it's always done. Make sure that low priority group, group number 4, is in the back. Now, let's draw the mirror image of this bad boy right here. Okay, so assign priority groups. Okay, 1 to 2, 2 to 3, and then back to 1. 1, 2, 3, 1. 1, 2, 3, 1. Now, my marker or highlighter or whatever is going clockwise. When you're going clockwise, you are R. So that's how it works. Now, counterclockwise is S, clockwise is R. Now, here's how I remember this. It's a little trick. If you go from 1 to 2 to 3 on this particular one, right? If I was driving in my car and turning my steering wheel that way, in this direction, clockwise, my car would go to the right, as long as you're going forward. Okay? The car will go to the right. R, right. And if you're not R, you're S. That's how I remember it. That's how I remembered it when I was a student. So if I'm going this way, I don't know if it works in the video or not. If I'm going clockwise, that's to the right. That's R. If I'm going counterclockwise, that's the opposite of R, so it's S. Okay? And that's how I do it. Let's do another example, because you can never do enough examples of stereochemistry, that's for sure. All right, let's do a skeletal formula. So here we have a skeletal formula. Now you have to know that there is a hydrogen right there. It's not drawn in. You have to know it's there. Okay, so there's a chiral center. The chiral center is right here. Let's assign priority groups. Well, to do that, we jump out one atom. When we do that, we see that it's bromine versus hydrogen versus, let me do this differently here, sorry, versus hydrogen versus carbon versus carbon. Very, very quickly we see we have a tie, so we're going to deal with that. Not a problem. But bromine and hydrogen, we can easily deal with that. Hydrogen is group number 4. Bromine is group number 1. Just as I said, usually 1 and 4 are easy to figure out. It's 2 and 3 that always give you problems. So now, let's worry about carbon versus carbon. So I went here and here. So remember, there's 2 hydrogens on here, and there's 3 on here. So it's going to be hydrogen, hydrogen, hydrogen for here. And the other one, this one, is going to be hydrogen, hydrogen, and carbon. So from here, I can go to hydrogen that's not drawn, hydrogen that's not drawn, or a carbon that's over here. From here, I can go from carbon to a hydrogen, or a hydrogen. Now, if you don't see those hydrogens in your mind, you should draw them in. I'm not going to. I'm going to keep this example a little challenging. If you can't already see the hydrogens that I'm talking about, you need to draw them in. And there's nothing wrong with that. Go ahead and do it. That way you can see how I'm getting 3 hydrogens on that carbon that I can jump to, 2 hydrogens on this one, and another carbon that I can jump to. If you can't see it, draw it out. Okay? Don't hesitate. Just draw it out. Pause the video, Draw it out. You'll see it if you draw it right. So now we can see from here, 3 hydrogens here, 2 hydrogens here, and a carbon. So this hydrogen and that hydrogen, no help. This hydrogen and this hydrogen, no help. However, hydrogen versus carbon, there's a difference. Now we know that this is priority group 2, and this is 3. So draw your arrows from group 1 to 2, 2 to 3, and then back to 1. This is the R configuration. That's the R configuration of that molecule. Okay, that's how you do that one. Let's do another example. So I made this one pretty tough, because it's always good to do tough examples, right? We have multiple bonds, and the hydrogen is not in the back. So here's group number 4. We all can agree on that, I think. That's prior to group number 4. It's not in the back. So before we can assign R and S to this molecule, we have to move it to the back. We can also assign, I think, priority to this OH, because we know that if we jump out one atom from here, it's going to be hydrogen, oxygen, carbon versus carbon. Let me draw that out just in case. Hydrogen versus carbon versus carbon versus oxygen, right? Hydrogen, carbon, carbon, oxygen, just jumping out one atom. So now, 4 and 1, as always, I shouldn't say always, but as typical, very easy to assign, 1 and 4. It's 2 and 3, they always give you problems. So now, let's examine these two groups extremely closely. So, R, which is where the chiral center is, carbon, carbon. So I'm just drawing out the ethyl group. So I just took this group and I drew it out, expanded over here. That's all I did. So this group right here, I drew it out, expanded over here. No problem. Now this group, I'm going to draw out doing what Kahn, Ingold, and Prelog have said we should do. There's my chiral center. So R contains the chiral center. Carbon, carbon. So let's call this carbon number 1, carbon number 2. 1 and 2. Carbon number 1 has a hydrogen on it. Carbon number 2 has 2 hydrogens on it, just like that. Now carbon number 2 is bonded to carbon twice. So let's draw in another carbon. Carbon number 1 is bonded to carbon twice. Carbon number 2 is bonded to carbon twice as well. So let's put that carbon in. There we go. So far so good, right? We have our ethyl group drawn out, and we drew out the alkene the way Kahn, Ingold, and Prelog said we should. Right now, we're here. We're on that carbon, waiting to jump out to another atom to find the difference so we can assign R and S. So now, from this particular carbon, we can jump out to carbon or hydrogen or hydrogen. Let me circle them. This one, or that one. We can jump out. And those are the atoms we can jump out to. From here, we can jump out to carbon, to hydrogen, or to carbon again. Hydrogen, carbon, carbon. So let's circle those. Hydrogen, carbon, carbon. All right, so now look at them. So this hydrogen and this hydrogen kind of cancel, if you want to say it that way. This carbon and that carbon, they cancel out too, so get rid of those. So there's no help there. But the help comes now. This carbon versus that hydrogen right there. Carbon has a higher priority than hydrogen. So therefore, this is priority group 2, the alkene. Now take your pencil, marker, highlighter, whatever, from 1 to 2, from 2 to 3, and 3 back to 1. You don't ever count 4. Oh, wait, no. Priority group number 4 is not in the back. Oh, can't do it quite so easy. See how quick it is? Students do this all the time. That's why I showed it to you like that. Don't do that. Always look for group 4 and say, is group 4 in the back? Because if it's not, we have some work to do. Thought we were done, but no. We can handle this though, guys. Don't worry. We got this all day long, all day long, all day long. So what I'm going to do is, if you have a model kit, this is a great use of a model kit too. What I'm going to do is I'm going to take an imaginary hammer and an imaginary nail, and I'm going to put it right through that carbon. And I'm going to say that carbon is, then this whole group is not going to move. So this whole group is stuck. No problem. That whole group is stuck. So let's redraw that molecule down here with that group stuck in place. So there's the carbon. This carbon and that carbon are the same. This whole group is in exactly the same location. So now, this is my point of rotation. So everything is going to rotate about this carbon. So now, this hydrogen has to go back here. This hydrogen has to go here. By the rule, has to go in the back. Hydrogen must go back here. Hydrogen must go back here. So if you think about this, in order to get that hydrogen back here, we have to rotate the entire molecule. So let me see if I can draw that on here. We have to rotate like that. So the ethyl group has to come forward, the hydroxyl has to go up, and the hydrogen has to go back. So I'm just going to draw exactly the same wedges and dashes. So notice, let me just get rid of that arrow real quick before I do that. There we go. So now notice, I'm going to draw the wedge in exactly the same location as the top one, as the red one. The dash is also in the same location, and the line up is in the same location. Everything about this is the same as this so far. Everything is the same. The only thing different is, where am I going to place these bad boys right here? Where am I going to put them? The hydrogen has to go in the back. I'm rotating this. I'm rotating this. The hydrogen has to go to the back. So when the hydrogen goes to the back, the ethyl group comes to the front. So the ethyl group is here. And when the ethyl group comes to the front, the hydrogen goes to the back, the ethyl comes to the front, the OH goes on top. And there you have it. That's how you rotate it. To get the low priority group to go to the back, that's how you do it. Put in your priority numbers, 1, 4, 2, and 3. Now we can do the whole 1 to 2, 2 to 3, and then 3 back to 1. Now we can do it and get to the right answer. 1, 2, 3, back to 1. 1, 2, 3, back to 1. So this is R. That's the R configuration of this molecule. Let me put it up here where you can see it. There we go. That's the R configuration. Now this question was very involved. A lot was going on with this example. So don't beat yourself up if you don't know how to do it right now, or if you're completely overwhelmed. Pause the video, try this question on your own. If you can't do it, try this one on your own. This is an easier one. If you can't do this one, go back to one of the other examples that were much easier. Make sure you can do these, because these are fundamental questions. They're not hard, but you got to practice them. If you don't practice them and the first time you're trying to do ones on the exam, I pretty much guarantee you're going to get it wrong, because it's one of these things that you have to practice. Let's do another example. We did 2. Let's do some more, because more examples are better, especially with stereochemistry, because it's really easy and I want you all to get it right. Let me think of a harder example, something that's going to give you some, nightmares when you wake up at night. How about, I'm just kidding. How about, Something like that. Now, it's not very hard. I think most of you are going to say this is pretty easy. But I have it here to emphasize a point. Notice there's no hydrogen on the chiral center. There's no hydrogen at all in the chiral center. So now assigning group 4 might be a little bit more challenging. And I'm using this as a great example of don't fall into the trap of always thinking there's a hydrogen. Because sometimes chiral centers don't have them. And that's okay. So you have to do what? You have to find the chiral center and jump out through the bonds in all directions to whatever atom's attached to the bond. So from here, we jump out to oxygen, sulfur, carbon, and boron. So it's going to be oxygen versus sulfur versus carbon versus boron, right? If you don't already know, of all of these, sulfur has the highest priority. Sulfur has the highest atomic number. If you don't know that, look in the periodic table. You'll see that it's under oxygen in the periodic table, so therefore it has to have a higher atomic number. Boron is group number 4. Boron's in group 13, where carbon's in group 14, and they're in the same period. So boron is actually group number 4. So this worked out pretty well. Group number 4 is already in the back. Can't argue with that, right? And now, so we've assigned 1 and we've assigned 4. Now it's oxygen versus carbon, which obviously 2 goes to the oxygen and 3 goes to the carbon. Okay? So now 1 to 2, 2 to 3, then back to 1. 1, 2, 3, back to 1. 1, 2, 3, back to 1. So this is S. Let's do another example. Let's do something that's a little bit challenging. Okay, so now we have a molecule that's chiral. It has 2 alkenes on it. And, ooh, that's going to be tough. But we'll have to handle it. So this is 1 and this is 4. 1 and 4 are almost always the easiest to assign. Let's take a look at this group and compare it to that group. And let's make the second group purple. So we'll draw 1 in blue. We'll draw 1 in purple. So R, that's where the chiral center is. Carbon to carbon. Let's call this carbon number 1 and that number 2. See a different color. Let's use blue. 1 and 2. So 1 and 2. Carbon number 1 is bonded to a hydrogen. A bromine on carbon 2. 2 bromines actually on carbon 2. And carbon number 1 is bonded to carbon twice. Carbon number 2 is bonded to carbon twice. So there we have it. The red one, or sorry, purple one, pardon me. The purple one, carbon to carbon. Let's call this carbon number 1. And carbon number 2, so 1 and 2. Carbon number 1 has a bromine on it. And carbon number 2 has 2 hydrogens on it, right? There we go. And let's change something real quick. Let's put the bromine up here. And let's put this carbon here. There we go. Make it a little cleaner. And carbon. So I think hopefully you guys are all old hat at doing the breakout that Conning Gold Pralog says to do. Hopefully you're all old school now. It's nothing to you guys. So we're here in terms of counting priority. I can jump out to here, or to there. So let's circle that. Here, here, or here. So hydrogen versus carbon versus carbon. So here I can jump out to carbon, carbon, or bromine. So let's circle that. Carbon, carbon, or bromine. So now, carbon versus carbon, no help. Same thing, keep going. Carbon versus carbon, no help, doesn't matter, keep going. Haha, here's my difference. Bromine versus hydrogen. So believe it or not, this group has a higher priority. Now I know this one has more bromine. I know that. But this one has the bromine closer to the chiral center. Therefore, this one, we found a difference early on. We didn't have to go to these ones. So this has a higher priority. So this is priority group 2, and this is priority group 3. Doesn't matter that there's more bromine on it. Makes no difference at all. Okay? So now, we need to rotate this molecule to put the priority group number 4 in the back. So let's drive a hammer and nail through priority group 1. So we're going to drive a hammer right into here. Just hammer and nail there. This OH is not going to move. And draw everything else the same. Let me move this up a little bit to have some more room. Everything else is the same. All the wedges, all the dashes, 100% the same. So now, we're going to rotate to put the priority number 4 in the back. So the hydrogen comes back here. This priority group 3 comes to the front. So let's do that. So this group went back there, this group came to the front, and that one went over there. And there you go. That's how you'd rotate it. So this is group number 1, group number 4, group number 2, and group number 3. 1 to 2, 2 to 3, and then back to 1. 1, 2, 3. So this is S. And that's how you would assign R or S to that particular molecule. Now, guys, you really got to practice this. There's lots of practice in this course, so please make sure you do it. This is not a hard skill to master, but it does take a minute. So give yourself the time to learn it. All right, real quick. Properties of enantiomers. Same boiling point, same melting point, same density, same refractive index. Same physical properties. All of their physical properties are the same, except how they rotate plane polarized light. That's one. One enantiomer will rotate light to the left. One will rotate light to the right. And they have different interactions with other chiral molecules. Now, think about this for a moment. Enzymes are catalytic proteins in your body. They recognize enantiomers. They can recognize one enantiomer over another. That's why, for example, your body, for the most part, only has one enantiomer of every amino acid, because the enzymes in your body are made from those enzymes, from those amino acids. Those amino acids are chiral, therefore your enzymes are chiral. Your enzymes can only recognize one type of molecule, one type of enantiomer. One, either the R or the S, they can only recognize one because they interact differently. This chiral molecule interacts differently with this chiral molecule. Now, if you don't believe me, it's called a handshake experiment. Now, I can't shake your hand because I'm on video, but you can find a friend or a family member. I want you to shake their hand as you normally would. Right hand to right hand, for example. They fit nicely. Your right hand fits nicely into the right hand of another person. Fits naturally. Now, in the pair of you, in the combination of the two of you, one of you change hands. Only one of you. So say, for example, your family member changes hands. So they were shaking their right hand to your right hand. Now I want their left hand to your right hand. Notice how that doesn't work so well. Because remember, your hands are chiral. Their left hand is chiral, their right hand is chiral, and your right hand is chiral. So your right hand is chiral. It interacts with their right hand in one way. It interacts with their left hand in a different way because they're chiral. So enantiomers are the same thing, same physical properties, same all of this, except they interact differently with other chiral molecules, as I just showed you with the handshake experiment, and they rotate polarized light the same magnitude but in different directions. And that's the difference between, those are the only differences in enantiomers. So here's what we mean by rotating light, polarized light. So we have our light source here that travels through a polarizing filter, which will take all the light that's more or less scattering all over the place. So light's just kind of scattering in all wavelengths. It's kind of randomized. It goes through a polarizing filter where the light now will become lined up. So only light that's vibrating in a certain way will make it through the filter, and we represent that by a line going straight up and down. So now the light is only vibrating in one direction. So all the light you're seeing vibrates in one direction. So now, here comes that polarized light, all vibrating in one direction. It hits your sample. It hits your chiral sample. And when light, polarized light, hits chiral things, it starts to rotate. Okay? So this light, as it's traveling through our sample, is rotating in one direction. It's rotating to the negative direction. Okay? And you can witness that. You can watch it. You can see it. It's very simple. In fact, if you're taking organic chemistry lab live with one of your faculty members at Broward College, you will see that. We have an experiment where we show it to you. That light, when it's polarized, is straight up and down. As it travels through the sample, though, we can measure how much it rotates to the left or to the right. Now, when light rotates clockwise, that's called a positive rotation or dextrorotatory. When light rotates counterclockwise, that's called levorotatory or negative. It's a negative rotation of light. Okay? And that's where you probably see it on labels, plus or minus some amino acid, or D versus L for something. You may have seen that on product labels. This is where they're coming from. Plus means positive rotation, negative means negative rotation, D means dextrorotatory, L means levorotatory. That's where these things are coming from. You may have seen these on labels. If not, go read some nutritional supplement labels, especially amino acids, and you'll probably see these. Okay, you may not, but you probably will. That's where they come from. They're just talking about enantiomers. Racemic mixtures. Now, you can get a mixture. In fact, it's very common, especially doing chemical reactions if they're not done in a certain way. You can get a mixture of enantiomers, 50% of one, 50% of the other. So a racemic mixture will have 50% of one enantiomer, 50% of another enantiomer. And that's called a racemic mixture. 50% of one, 50% of the other. Now, in a racemic mixture, the optical rotation will be 0 because this enantiomer will rotate light, say, for example, 5 degrees to the left or counterclockwise. This will rotate at 5 degrees clockwise, so they actually will cancel themselves out and produce what appears to be 0 rotation of light, although it's just been canceled. The rotation of light's been canceled, so the observation is no rotation. You could have the same boiling points in a racemic mixture as an optically pure molecule or melting points, but you may not. They may be suppressed because you have a mixture of molecules.